Good morning, everyone. I'd like to welcome you to today's DBA Administration Virtual Chapter presentation. Today's topic is indexing for performance, and we're very lucky to have our speaker today, Jeff Garvis. He's well known in the community, and today looks forward to be a really great presentation. It will probably be the full hour and then a little spillover, so we can try and plan accordingly. We're going to queue all questions to the end, but please submit them throughout the course of the presentation. And yes, my name is Mike Clark, and as always, our virtual chapter presentations here for the DBA BC is sponsored by Dell Software. Technology makes things many times less expensive, and online presentations are even a little bit less expensive, but there are costs, and Dell helps offset those costs, and we appreciate it very much. Want to have a shout out to Dell Software. This is part of SQL Pass, and SQL Pass is all about the SQL Server community and bringing people together and training and mentoring, as well as just overall community kind of a presence. There are SQL Saturdays that will be coming up. What a SQL Saturday is, it's basically kind of in the name. It's a SQL Server training on a Saturday. And so they're all-day sessions. They're generally free. Lunch is provided. And it's a great high content. And I'm sure Jeff has spoken at several of those around the U.S. and maybe internationally. And so there's some here coming up in North America. There's one just down the road for me this weekend in Sacramento. One of my old stomping grounds back in New York also on the 25th. But there's several coming up internationally too this weekend in Manchester and Odessa. So if you want more information, you can go to SQLSaturday.com. You can see all the ones that are scheduled, even out further than August, and you can start planning a trip or presentation. They are open for folks to present. One of the largest events, or the largest event for SQL Pass, is actually the Pass Summit. It's an annual summit. It's quite large. I've gone probably 8 or 9 years in a row. Right now, they still have a discount in effect for our virtual chapter. So if you go register and enter in that discount code on the page here, VC15FPS6, you'll get a $150 discount. It's a great event. If you want more information, you go to SQLpass.org and click on the big advertisement there for Pass Summit, and you can find out all the topics, the speakers, and any costs and accommodations that you need to figure out. Again, it's probably the most cost-effective way to be trained in SQL Server and to meet fellow SQLites. So we do appreciate you coming to the DBA virtual chapter, but there are more out there. So if you have other interests besides DBA, which I know this is the key one for everyone on the planet, but we do have tertiary interests, and so there's plenty of them. And if you have an interest that's not yet captured in any of the virtual chapters, again, you can go to SQLpass.org and enter in a request to create one of those, and you might very well be the leader of it. That's just how a volunteer organization works. You have an idea and have the passion and the energy, and you can make it work. Like I said, we are a volunteer organization, and everything is done by volunteers. There's a small core of paid folks that kind of just keep the lights on, but pretty much everything else is volunteer, including the board. So if you have any interest in time and you want to lend a hand to the SQL Server community, again, you can go to SQLpass.org and click on I want to volunteer, and we will take you up on that offer. We appreciate all the help that we can get. So stay involved. That's a big key. There's many different ways to reach out in the SQL Server community. This virtual chapter is one of them. It's LinkedIn, Facebook, Twitter, and then actually the website. I've mentioned it several times. SQLpass.org is pretty much the launching pad for everything related to our organization. You can get the SQL Saturday links from there. You can get the other things that we have going on. All the virtual chapters are represented there. If you forget everything else about today, SQLpass.org is this place you want to go to. But to circle back on why we're all getting here today is we're want to learn about indexing for performance, and we have a good teacher from Jeff. Jeff's been consulting on this stuff for quite a long time. He's been with SQL Server since 1989. That's a long time ago. Version 4 on OS2. OS2. Man, I'm sorry. I read that and I'm like, wow. Anyway, I was around then, but it's been a long time since I've heard those phrases. Since then, he's been working quite a bit with each of the releases and the product. He's kind of focused his time on performance and tuning from all sizes of applications and companies up to, from startup companies and their applications to multi-terabyte data warehouses. We've known him for a while. He's spoken at many of our conferences and so forth. He's written extensively. He's got 19 books. And here's another piece of trivia. He was certified to teach SQL Server back in 1989. That's amazing. He's been doing this a long time. So we're looking forward to a great presentation today. And with that, Jeff, I am going to make you presenter, and we'll continue on. Oh.
Thank you very much, Mike. Appreciate the time and the kind introduction. You're right, I have spoken a lot of SQL Saturdays, starting with SQL Saturday number 2, which was in Tampa. And I think I'm up in the 40 to 50 range in terms of the number of them I've spoken at, and in particular, this one has been presented a lot of them. In fact, I had an interesting surprise at one of them. A gentleman came up to me and said, Jeff, this is the 5th time I've seen you do this presentation. And I was surprised that somebody came up to see it a second time. And he said, I learned something different each time. So apparently people are seeing value in the indexing for performance presentation. So I hope you're all enjoying yourselves. My name again is Jeff Garbus, and because there are so many attendees, we're up at about 200 right now. I will ask for the questions to be held until the end. When we have a smaller group, I let folks interrupt me, but let's just get through all the material and then start doing some clarification. This particular presentation is an hour out of a 5-day class I have, which is a basically performance and tuning class for developers, although DBAs have loved it as well. This chapter is everything you wanted to know about indexes but were afraid to ask. We talk about everything from how the optimizer selects indexes to how the index physical structure looks to how you want to be able to use the optimizer's use of the index to your advantage. So that said, I'm going to dive right into it. This is a little bit about Soaring Eagle. If you really care about this, come back and see the recorded message. Basically, we're a bunch of database geeks that do consulting, training, and managed services. But I'm just going to dive directly into indexing as a topic. Now, before I start getting into the slides, I'm going to come off the deck for a minute and talk about what indexing really is. So, from a practical standpoint, an index is a mechanism to get at a particular piece of data as quickly as possible. There are secondary uses for indexes. For example, an index may be used to enforce uniqueness. But in general, if you have a large amount of data, you don't want to wait days and days to get it. So, if you have, say, 1 billion rows of data, which is not unusual these days, what are your choices? Well, you can use a table scan to get the information. Table scan of 1 billion rows is going to take a little while, even if you've got flash storage or some sort of solid state equivalent. Or you can use an index. We'll talk about what that means, how it looks, what the various index structures are, clustered versus non-clustered, how the optimizer can and can't use them. But let's talk about how to conceptualize an index first. The example I've been using for years and years and years is a telephone book. And telephone books are one of those things that I'm not sure my kids know what a telephone book is because they look everything up on Google on their phones. But for those of us who are doing this, you're probably old enough to remember what a telephone book is. A telephone book is a mechanism to bring back a telephone number and an address based on the key of last name and first name. So how does a telephone book really work? When I'm trying to find me, Jeff Garbus, in the telephone book, I take my thumb, I run it across the top of the pages, and I open them slightly. And I scan very fast until I get to the G's, and then I slow down more at GA, then I slow down more at GAR, and then I plop the book open. Plop being one of my technical words. Then I take my finger, which is my pointing device, and I run it down the side of the page until I find GARB, then GARBU, then BUS, and now I have that first key column, which is garbus. Now, there are probably multiples in there, and what I'll do then is find Jeff. So I move my finger to the right, the next column, and start moving down that list until I find Jeffrey. Once I find Jeffrey Garbus, I can go off to the right, which is the data that I'm looking for, which will bring back the address and telephone number. So the telephone book lookup really is an index on last name, first name, middle name, which returns an address and a phone number. Now, I'm going to take that analogy and I'm going to beat it to death, but I'm going to beat it to death with malice aforethought. So let's think about that analogy for just a little bit. If I have a telephone book, and if you think about that telephone book as an index, which it is, let's ask some questions surrounding the use of that index. First question I'm going to ask is, what if instead of looking for Jeff Garbus, I'm just looking for all the Garbuses? Is the telephone book a good lookup for all the Garbuses? If you think about it, it really is, because I can still use my thumb to get me to the first page that the Garbus is going to reside on. I can still use my finger to get me down to the first Garbus. And then what I can do is, rather than moving to the right, picking up that second column, I can just keep reading down and picking up each Garbus, going off to the right, getting the address and telephone number, until I've brought all the Garbuses back, and as soon as the name changes, I can take the Garbus and say, okay, I'm done with the telephone book. So if I'm using that first column of the index, that index is still a good lookup for that last name. Now, taking a look at a second analogy, or rather a second beat-up of that analogy, what if instead of looking for last name, I'm just looking for first name? Bring me back all the Jeffs. Do you want to use a telephone book to bring back all the Jeffs? Well, probably not, because what you have to do then is to turn every single page of the telephone book to identify whether each single entry has a Jeff in it. We don't have a good lookup for that in the telephone book. Now, when we come back to the index analogy, that works exactly the same. If I have an index on A, comma B, and I want to do a lookup on B, that is not a good index to use for B. That said, it's amazing how often somebody will say, Jeff, I've got an index on A, B, and C. I'm trying to do a lookup on B, and it's not using the index. Why not? I come back and I use this telephone book example. So what if we have the telephone book, and the telephone book is on last name, first name, but I do want to do the lookup on first name, because I frequently say, I want to get all the Jeffs. Well, in that case, what we're going to do is create a new index, a new telephone book. That new telephone book will have an index on first name. But if we come back to basic relational theory says only store the data one time. Why am I bringing this up? Well, from a practical standpoint, what it means is that when I have a separate telephone book that does the lookup on first name, I'm not going to have the address and the telephone number in that same page. Instead, what I'm going to do is I'm going to have a reference to the page and row that that entry is on in the main telephone book. I'm going to state this all a bit differently. I want you to visualize that telephone book as a clustered index, because the data is on the same page as the index. That leaf page of the clustered index is the data page. The non-clustered index, that smaller book, is the lookup which gets us to the page based on a different key, based on that first name. Now, hold those ideas in your head, and while you're doing that, I'm going to ask yet another question, which is, why is the telephone book indexed on last name, first name, and not first name, last name? Now, there are some potential sociological answers to this. Well, in the olden days, you always called somebody Mr. Smith or Mr. Jones. That's not it. Is this failover from something British? Bond, James Bond. No, it's not that either. What we find is that the granularity of the data, the cardinality of the data, makes a great deal of difference in terms of the efficiency of the index. If I'm doing a lookup on Jeffrey Garbus and I'm going to find the Garbus, how many Garbuses are there in the phone book? Well, generally not very many. As a result, when I zero in on that Garbus, I only have a very few entries to check to look for Jeffrey. Now, if we turn that around and ask how many Jeffreys are there in the phone book, the answer is generally going to be quite a few. In fact, what I've found in real life is that if any group has less than 10 people in it, the chances of having 4 Jeffs are greatly improved. In this group of 200, I'm willing to bet there are several Jeffs, but that I'm the only Garbus, just in terms of granularity. So if we were indexing on first name, comma, last name, I'd have a lot of Jeffreys to go through before I found the first Garbus. As a result, as we start thinking about the index, we don't always have a choice, but when we have a choice, we want to lean towards having the more distinct column first and the less distinct column subsequently. So, I think that's my last telephone book example for the moment, although I reserve the right to come back to it. What I am going to do now is start coming to the more specific topics and also the more SQL Server specific topics. So we'll be talking about search arguments, that is to say, how we're going to restrict the data coming back from the table. A search argument is almost a requirement for using an index. We'll talk about clustered versus non-clustered, ands versus ors, index covering, forcing index selection, and filtered indexes. So the server's got 3 basic search techniques for query resolution: table scan, index search, and a covered index search. A table scan says, I'm going to identify the first page in the page chain. All pages in SQL Server, all tables in SQL Server are stored in pages. A data page is currently 8K in size. With this 8K page, we're going to stick as many rows into it as we can. Stick being one of my technical words, and as many rows as we can being a vague reference to the fact that the more full the page is, the fewer pages we have to have in case we're doing a scan. Now, we do have issues of things like fill factors, and those are a bit out of scope for right now because we're talking about index selection as opposed to index maintenance. So let's stick with table scans. With a table scan, I'm going to go into a system table, identify the first page in the page chain, read it in. Get the data off, check the page header. The page header is going to have a pointer to the next page. I'm going to go grab the next page, bring it in, and I'm going to keep performing this loop until I hit the end of the page chain, which is to say that next page pointer happens to be null. A scan is expensive compared to using an index, but it may be the best way to resolve a query. If I say select star from the table, I don't have a where clause, there's no reason to bounce in and out of an index structure. The table scan is going to be that much faster. If you do have a clustered index on the table and you do have some sort of an index that matches your query, we may do a partial table scan. So let's say I'm indexed on last name, first name, and I want to bring back everybody whose first name starts with a G. Well, at that point I can use the index to get to the first G, then I can table scan until I get to the first H, and then I can stop. Here's an example. I'm saying select star from the table where the ID is equal to 1. In this case, ID equals 1 is the search argument. We're using it to restrict rows coming back. But we have no index on ID equals 1. So we're going to do a table scan. Note that the table scan is the most expensive component of this particular query plane. One of the other things that I do, and this is very old school, it's been around since the 4.01 days, is set statistics IO on. What this does is it tracks the number of times the table is scanned as well as the number of page requests that we make. In general, I tend to cost a query based on the number of page requests that I make. 1 million page requests is going to take a finite amount of time, but it's easier to measure than how many were physical and how many were logical, which can be, varied by a lot in a real-time system. So, what we see here, we set statistics IO on prior to running the query. When we run the query, it says I have a scan count of 1, logical reads of 38, physical reads of 0, and read ahead reads of 0. Let me translate that because these numbers are all relevant to me. Scan count is a number of passes through a table. Why might we pass through a table multiple times? Well, Maybe I have a select with a where clause, and the where is performing an aggregate, and I have to go pass through the table to resolve the aggregate, and then I pass through the table to check it. Why else might I have a scan count greater than 1? Maybe I'm doing a join. If I'm joining from table A to table B, for each row in table A, I need to bring the matching rows in table B, so I may need to scan table B multiple times. A logical read is a page request. A physical read means I had to go off to disk to resolve the page request. Why is this relevant? Well, from a performance standpoint, once I start working on a query, most of the reads are going to be logical. So overall, I want to pay attention to the number of page requests that I'm making. From a real perspective, a physical read is very, very costly. Why is that? Well, because the read time is so long compared to anything else that we do, what's going to happen is something along these lines. I identify that I look for the page in cache, it's not there. At this point, I queue the page to the I/O subsystem. Once I queue that page to the I/O subsystem, I swap the process out. Once the page comes back, the process goes from I/O wait to available to be processed. And then I will swap it back in. That process of swapping things out and back in is cheap compared to the cost of waiting for the I/O, but it's very expensive compared to the logical reads. When physical reads are high in an OLTP system, I will start to think in terms of more memory. Now, I do have another presentation I do on how I make those types of determinations, but the short version is if I have a high memory paging rate, high defined as 200 or 300 a second, or if I have low page page retention, that is to say the page retention is less than, a couple thousand seconds, I tend to think in terms of more memory. Finally, we have a read-ahead read. A read-ahead read is also called an asynchronous prefetch. The idea behind the asynchronous prefetch is, rather than going through the read a page, swap the process out, read a page, swap the process out, continue for, a billion page reads, we can go through a request a page, request a page, request a page, and start processing them as they come in. So a read-ahead read is a performance benefit and will be performed under very specific situations. Obviously, if I'm not doing any physical reads, there's no reason to do the asynchronous prefetch. Note that a table scan can also be performed at update time. Here I have an update table. I'm incrementing all the IDs. Note that the cost of the table scan is about 80% of the query, and the cost of the update is about 20% of the cost of the query. Note that we're not necessarily modifying the physical pages, but we are certainly logging all the changes and physically representing the changes to the log. Note also, if you're updating a table, you are going to lock the entire table for the duration of the update, even if you're only modifying one row if you don't have a matching index. So this table scan is going to cause a problem, potentially. I've had that, by the way, be a cause of client performance emergencies many, many times over the years, simply not having a well-matching index for an update. Now, here's another interesting trivia question while I'm here. I'm performing an update, set ID equal to ID plus 1. Now, in real life, you're not going to do something like this generally unless your resume is up to date and you're getting ready to change your name. But from a practical standpoint, it is interesting to ask the question, will this work if I try to do it? Well, from a practical standpoint again, yes, it will. So let's say, for example, I have a unique index on ID. The IDs start with 1, 2, 3, and I want to make them 2, 3, 4. Why would we want to do this in real life? Well, your company buys another company. You have customers numbered 1 through 1 million. They have customers numbered 1 through 1 million. What are the chances that your customer number 1 corresponds with their customer number 1? Pretty slim. So what we want to do is increment all their customer numbers before incrementing them, putting them into our customer table. But the SQL Server will do a thing called a deferred update. The deferred update says, let's identify all the changes and make all the changes, at least in memory and within our transaction prior to testing the referential integrity constraint. That gets us through this immediately. So let's start moving to how the indexes actually work. We'll talk about index selection criteria, when the indexes slow the access down, and some index stats. So I'm going to start with the middle one. When do the indexes slow access down? Well, every time you insert a row, you need to insert a row into an index saying this is how to find it. If you have two indexes, you have to insert two index rows. If there's any page splitting going on, that has to happen too. If you have 10 indexes, 10 additional inserts. You're starting to see a pattern here, I'm sure. One of my favorite calls, I get a lot of these calls. I've done this particular seminar lots, and I've probably trained 3,000 or 4,000 people over the years. So what ends up happening is I get these calls out of the blue. Hey, Jeff, somebody told me that you can fix my performance issue. And I always say, well, who recommended me? Because I'd like to send them a bottle of wine to say thanks. And only about a third of the time do I get to send a bottle of wine out, which is, to me, just sort of strange. But I always try to help. But in this particular occasion, it was a company out in eastern Long Island. They said, our inserts are taking 3 to 5 seconds. And my first question was, what are you doing at the same time? What else is going on in the box? They said, nothing. We're doing this in isolation. And my next question, this was late on a Friday afternoon, and it had been a long week, and I wasn't as polite as I normally am. Instead of asking, do you have a trigger on the table, I said, what's the trigger doing that's on the table? And they asked, how do I tell if there's a trigger on the table? And I said, there's your first problem. Let's go take a look. And there was no trigger on the problem, but we're still experiencing 3 to 5 seconds for the updates. So my next question was, how many indexes do you have on the table? They said, how do I tell? And I said, there's your next problem. We went out and took a look. They had 120 indexes on the table. For those of you who are whistling and I can't hear you, you're absolutely right. That is a huge number. And that means that for every insert, we need to make adjustments to 120 separate physical index structures. This was an older box. This was a while ago. They were all IDE spindles. And what I said was, 3 to 5 seconds is actually not bad. Particularly considering I bet you've never rebuilt your indexes. And they said, what's that? And I said, there's your next problem. But their biggest problem was way too many indexes. In an OLTP system, the old rule of thumb used to be no more than 4 or 5. These days, I frequently see 10, 15, 20 indexes on a very high volume table without causing too many issues. And my own rule of thumb tends to be, if I'm experiencing a severe performance issue, I will add another index as long as I don't have another one very, very similar to it, in which case I'll modify the index. My other rule of thumb is if I see 20 indexes out there, I'll look to ask, A, are they all being used? Because we can pull that out of the system tables these days. And I will also ask the question, are any of them similar enough that I can combine them? And we'll talk about that later as well. And finally, index stats. So let's move on. During the index selection phase of optimization, the optimizer decides which indexes best resolve the query. I mentioned this is out of a class. In that class, we do talk about the phases of optimization. We identify which indexes match the where clauses and the join clauses. If they do not match a where or join clause, it doesn't make sense to use the index. We estimate the rows returned in the page reads. Why do we bother with this? Well, it's certainly possible that if I'm going after all the data, it's more efficient to do a table scan than to bounce in and out of an index structure. Also, when we start talking about join performance, what we find is that row to page ratio is very important when we start choosing join orders. So that said, how do we decide which index we're going to use? Well, an index is normally going to correspond with a search argument. One of the things we talked about when we were using that telephone book analogy, and remember I warned you I was coming back to it, was that if we're looking for Garbus in the telephone book, that's a good lookup. If I'm looking for just all the Jeffs in the phone book, that's a bad lookup. But guess what? If our choice is using the telephone book to find all the Jeffs or to dial every single number there is to find all the Jeffs, what's faster? Well, I'm going to turn every page of the phone book. Now, as you look at query plans, you will see multiple different types of index lookups. You'll see index scans, index seeks, and bookmark lookups. An index seek is a good thing. An index scan means You are turning every single page of the phone book to find the JEFs. The index is being used, but it is extraordinarily inefficient. That, by the way, is called a non-matching hash scan, for those of you who are geeks like me. For those of you who are not quite that big a geek, don't worry about it. The search argument is normally going to specify a boundary for the result set. Here I say where date of birth is between 3/3/1941 and 4/4/65. There are actually a couple of trivia questions behind this as well. The first is, will I use an index on DOB? Yes, absolutely. Next, why do I spell out 1941 and just say 65? There is a feature in the SQL Server that says if the date is less than 50, I assume it's 2000 and something. If it's greater than 50, I assume it's 19 something. So 65 being greater than 50 is assumed to be 1965. If I did not spell out 1941, it would think it was 2041. Next interesting trivia question, and it's rare that an entire room full of people get this one right. Let's say, just for the sake of argument, there's 10,000 rows between 1941 and 4/4/65. If I reverse these and say between 4/4/65 and 3/3/1941, do I get back those same 10,000 rows? Interestingly, I usually get about a half a dozen people who are confident that I don't, about a half a dozen people who are confident that I do, and the rest of the room, which might be 30 people or 300 people, tend to think, okay, what's the answer? One makes sense, but what's for real? And why is he bothering to ask this? Well, the real answer is it depends what version of SQL Server you're running. If you're running a version of SQL Server prior to the ANSI 89 standard, both results give you the same back. These days, you will generally get an empty result set because between is defined by the ANSI Standards Board, now the ISO Standards Board, as greater than or equal to the first number and less than or equal to the second. We will use DOB index because it is creating a boundary and restricting the number of rows that are coming back. Now, what we're going to do is create this index on last name and first name, and ask the question, is this index useful? You can answer this question by thinking about the phone book. So the first question is, I'm selecting the author where the first name is Jim and the last name is Smith. I sometimes have people look at this a little bit cross-eyed and ask, does it matter what order the columns are in when I create the index? And the answer is, absolutely from a performance perspective, but not at all from a syntactical perspective. This first lookup is designed for that index, and it doesn't matter if I say first name, last name, or last name, first name. The second one is that non-matching hash scan. We might say index scan, which is generally a bad thing versus the index seek. But it is not a good lookup. Finally, last name is Smith or first name is Jim. If you think about that, what we really need is to bring back all the Smiths. We also need to bring back all the Jims. Is that a good index to bring back all the Smiths and bring back all the Jims? Well, not really, because it's not going to be efficient for bringing back all the Jims. We might just simply do a table scan and do a filter. Or we might do a non-matching hash scan and get that index scan coming through. So let's get into the index types, selection criteria, and stats. The server has three basic types of indexes: a clustered index, a non-clustered index, and a full text index. When we have a clustered index, we physically sort the data in the index order. Because we can only physically sort the data one way, we need to be able to create additional types of indexes. Those are the non-clustered indexes. We're limited to 248 of them. As I mentioned earlier, the more indexes you have, the worse your performance is going to be at insert, update, and delete time. It says full text is discussed in a later section. Well, we're not going to be getting to that today. From a practical standpoint, the full text index is going to let you do fuzzy logic searches of varchar max and text columns. I'm going to spend the next 10 minutes or so on the next two slides because this is where the importance is. If anybody is eating lunch, getting distracted, somebody's walking into your office, this is a good time to say, leave me alone, I'm busy, or if you're napping, to wake up. This is a graphical representation of our clustered index. Note, the data pages are physically sorted by the index. We have a clustered index here on last name. The way we build the index structure is as follows. We have a physically sorted set of data pages. To point to a data page, I really need only one pointer per data page. So what I'm going to do is I'm going to take the entry Albert from the first data page and move it to the intermediate page. And I take the first entry Brown from the next page, move it up. First entry from the next page, Exeter, bring it in. And I'm going to do this until I have the ability to point to every single data page. So I have one pointer here per page of data. Next, I have this basic intermediate page. What I need is an entry point. So I'm going to keep building these levels of index out until I have a single page, which is going to be my root page. I'm going to build these out exactly the same way. First entry, first entry, first entry. Now let's use the index. I want to find Joe Baker. Baker's between Albert and Jones. I follow the Albert pointer in. Baker's between Albert and Brown. I follow the Albert pointer in. Now I'm on the page with Joe Baker, which is what I've been looking for all along. This is a 3-page request search. Once I get to the physical page and the page is up in cache, it really doesn't matter if I scan the page, do a binary search on the page, check the row offset table at the tail end of the page and look to see where the row is on the page. This is the lion's share of the cost of the retrieval. Cost of bringing back Joe Baker, 3-page requests. Now, in addition to that clustered index on last name, I'm going to create a non-clustered index on first name. I need to be able to bring back everybody, and as a result, if I'm going to have pointers off to rows of data, I need a pointer per row of data. What does that mean to you? What that means to you is 1 million rows of data, 1 million index entries. Contrast to the clustered index, which is 1 million pages of data, 1 million entries. So a non-clustered index does tend to be bigger than the corresponding clustered index. Now, 1 million entries, 1 million rows, 1 million entries. Once we have this 1 million entries, we build this index structure out pretty much the same way we built out the clustered index structure. First entry, bring it in. First entry, next page, bring it in. First entry, next page, bring it in. And then we continue to build these intermediate pages out until we get a single root page, which is our point of entry. Now, let's find something in this non-clustered index. I want to bring back all the Amy's. Amy's between Amy and George, we follow the Amy pointer down. Amy's between Amy and Bob, we follow the Amy pointer down. Now that we're on the leaf page, we have our list of Amy's. So, we make a page request for each Amy that we find. In this case, I've got 2 Amy's, I make 2 page requests. What's the cost to bring back the Amy's? 3 page requests to get to the list of Amy's, and then 1 page request for each Amy that I find. Now, let's do some compare and contrast because we're about to get really, really interesting. What's my cost of bringing back 50 Joe Bakers? Well, let's throw some numbers in the air. We have 1 million rows of data. We're fitting, say, a 8K page. Well, maybe we've got 80 byte rows. We're fitting 100 rows per page. 50 bakers might be all on that same page. Well, if they're all on the same page, the cost of bringing back 50 bakers is 1, 2, 3 page requests. If they don't fit on the page, these are linked pages. I can read the next page and bring back Joe Baker. The cost of bringing back Joe Baker, on a good day, 3 page requests. On a bad day, 4 page requests. What does it cost to bring back 50 Amy's? 1, 2, 3 page requests to get down to the leaf page. then 50 page requests to bring back the data page. Note that those may be logical page requests, but they are page requests nonetheless. What if I have 1,000 bakers? Maybe 10 pages. 1,000 Amy's. 1,000 page requests plus. Once again, I'm sure you're starting to see the pattern. As we start increasing the number of rows that we're retrieving, this non-clustered index becomes less efficient. Let's say that we're not in a regular telephone book. Maybe we're at an Amy convention. Half the people are Amy's. Let's throw some more numbers into the air. We've got 1 million pages of data. 1 million pages of data represents 10 million rows of data. Sorry, 100 million rows of data. Of those 100 million rows of data, 50 million rows of data are Amy. So if I got 50 million Amy's and do 50 million page requests, what's the cost versus scanning 1 million pages of data? Definitely faster to scan 1 million pages of data than to make 50 million page requests. There's a 50-to-1 ratio. What we find when we do the numbers is that there is a gray line at about the 1% mark there. And that has to do with the ratios of rows on a page. Now, let's take this and take a couple of practical applications to it. And I'm going to start with my absolute favorite. I'm willing to bet that every one of you is familiar with a parent-child relationship, and I'm going to pick one that I like to use as an example, which is invoice header, invoice detail. What most of you have at your shops is a structure that looks like this. You have an invoice header. That invoice header has an invoice header ID. You have an invoice detail table because an invoice might have 50 line items on it. Well, in that invoice detail table, what you typically have is an invoice detail ID, which is usually an integer, and it's usually an identity column because Microsoft makes that recommendation. Then you have a foreign key, which is the invoice header ID. Now, when we go after all the invoice details for an invoice header, what's going to happen? Well, we have a non-clustered index on that foreign key. If we have an average of 50 page requests to bring back the 50 details, then to bring back all the details for the header, my cost is 50 plus the number of index levels. So 50 page requests, interesting. Now, what if we're running off all the invoices for all of our customers? That's a lot of I/O. What if we do the following? Instead of creating our primary key as a clustered index in the invoice detail table, we create the primary key as a non-clustered index. Then we create the foreign key of invoice header ID, which is our general lookup, as a clustered index. Now what happens when I want to bring back 50 index detail rows? I'm guaranteed that they're all going to be on the same page. This is extremely cool. I just made my query 50 times faster by swapping the clustered and non-clustered index from the primary key, which we almost never use on that table, to the foreign key, which is how we're doing our lookups on that table almost all of the time. This is a single trick which can take your multiple hour reports down to seconds or minutes. Because not only are you making that 50 times faster, but when you do your lookup from your invoice detail to the pricing table, to the discounts table, to the descriptions table, to the you name it, I bet you're doing those same types of lookups. My personal record, swapping one index like that. Great story behind it, which I'm going to share with you. I have this group in New York City that I've been working with for almost 20 years. They bring me back somewhere between once a year and once a quarter to do just an overall health assessment and review their system. On this one occasion, they brought me in and said, Jeff, I know we've scheduled you for this week, but we're swamped. We've got deadlines. You sit in your corner. You do your thing. Thursday, we'll do an evaluation. Friday morning, we'll roll everything out. And if everything is clean, you go home after lunch on Friday. We're still friends. We'll see you in 3 months. So Thursday night came. Friday went. I went home. I got a call on Monday morning. I don't know how many of you are actually in New York. I don't know how many of you have dealt with New Yorkers. And I say without any kind of capriciousness intended or any kind of slight or insult, that in general, New Yorkers are not a giggly group. This New York City mid-level manager called me up on a Monday morning and he was giggling. And I said, so Luis, what's going on? And he said, well, you caused us a major production issue on Friday night. Since he was giggling, I wasn't too worried. And I asked, what happened? He said, we have this report that we kick off Friday afternoon at 5 o'clock. It is mission critical for our entire company. And by the way, they manage $4 trillion in assets. This report goes all the way up to the CEO. Everybody uses it. The analysts use it. If it dies for some reason on Saturday or Sunday morning, instead of running the 48 hours, that means we're running the whole next week on the prior week's data. This is very bad, and heads roll. I said, so tell me what happened. He said, we ran this on Friday afternoon and it died. We ran it again and it died. We ran it again and it died. I was very polite. I did not mention Einstein's description of insanity, or definition of insanity. And I said, so what happened? He said, at this point we escalated. We escalated. By 7 o'clock, we called the CEO, who is on the call line for this, who had just stepped into the theater for a show, and we were on the call for another 2 hours until finally somebody asked, did anybody look for output? Nobody had, because this usually runs for 48 hours. We had taken, with one index switch, a 48-hour query down to 23 seconds. This query went from being a thorn in everybody's side to something that folks did what-if analysis throughout the course of the week. This is with one index change. Indexes can be absolutely mission critical, not only for reports, but for LTP processes. And knowing how the indexes work, how the index structures work, how they're organized, is absolutely critical to being able to make those types of decisions. Now, let's stay with this non-clustered index for just a moment and ask a different question. Instead of asking, bring me back the phone numbers and addresses for all the Amy's, I want to ask the question, how many Amy's do I have? In order to ask the question, how many Amy's do I have, do I really need to go down to that data page? I really don't. I can just go down the leaf page and count the Amy's and bring it back. This technique of treating the leaf level of the non-clustered index as if it is the data page of a clustered index is called index covering. If any of you have ever put a query in Query Analyzer and right-clicked on it and said display the graph, and the graph comes back with add this index and it will make your query X% more efficient, often there's an include. Create index A on columns this, include columns something else. Those include columns are bringing the data from the data page back up into the leaf page so that you have a de facto additional clustered index. Now, it increases your storage by a lot, but it improves your performance dramatically, absolutely dramatically. That's been a common trick forever, even though the include columns really didn't come in until about 2005, I think. So what we used to do is just simply bring them into the index structure. The nice thing about the include columns is that we don't sort on them, so they don't have to be volatile. So let's do a quick run through these. Well, I've only got 6 minutes left, and I have 43 slides to go through. So I'm going to start talking really fast, and we'll cover topics. The idea behind the clustered index is that we physically sort the data. This is great for ranges of data. The non-clustered index has to do the lookup into the physical data page for the clustered index. Clustered indexes are great for ranges. They're great for sequentially accessed columns, and joined columns. They're also great for static columns. Let's come back to the picture just for a second and ask what happens when Elizabeth Best marries Juan Nacelle. Most of the time, Elizabeth is going to change her name to nacelle, or best nacelle, or nacelle best. What that means is that that row is going to move, which means that the non-clustered index has to change. So when we choose a clustered index, we try to choose a non-volatile column. Other indexed columns, you don't make the indexes too wide. Note that the include columns do not count toward the limitations. One of the discussions that I frequently get into is people say, gee, doesn't the primary key have to be clustered? No, it does not. Gee, doesn't the clustered index have to be unique? No, it does not. A primary key can be clustered or non-clustered, and an index can be unique or non-unique, regardless of the type. Note that a primary key is a logical concept, not physical. An index is a physical concept, not a logical, although there is a strong overlap between the two. Note the comment down at the absolute bottom that you do get some overhead because the clustered index is automatically appended to other indexes for lookups. This is usually worth absorbing in order to get the best clustered index. Now, the next question becomes, how does the optimizer choose the index? And you've pretty much got that. The idea behind the optimizer choosing the index is that we need to be able to restrict the rows. So in the first example, we want an index on title. Do we want this on clustered or non-clustered? Well, clustered makes sense if that's a frequent lookup because it's non-volatile, or if it's the only index. We always want to have a clustered index on all of our tables because otherwise the data gets stored as a heap. And the next one, price between $5 and $15. There's an interesting lesson in that one and the next, which is how much data are we going after? We need to understand the data before choosing index, because the books between $5 and $15 that say at Barnes & Noble is going to be most of them. We do not want a non-clustered index just on price, although a non-clustered index on price include title works. Also, understanding the data between $5 and $15 might be the vast majority of the books at a Barnes & Noble. That's only a $10 range. But if you pick a $100 range between $500 and $600, there might not be any books at all in that range. So here's just some basic numbers we talked about. And again, I'll save this for those of you who want to go through the numbers in the presentation. You can always pause it later. Be aware that the clustered index versus the non-clustered index for ranges of data, very, very dramatic. And if you're using a non-clustered index and the optimizer is not choosing it, there's a good chance it's because it's going after too much data. So, for an OR, here's some basic rules. For an AND, we'll choose one index. Last name is Garbus and first name is Jeff. I want one compound index, or composite index, depending on the terminology you prefer. For an OR, I want an index for each component of the OR. So here I want an index on price and an index on type, and both should probably include title. The indexing for the OR, keep in mind that an IN is treated as an OR. Someday they'll take the IN and they'll build a temp table and they'll join off to the temp table, but I haven't seen that in a plan yet. So the last one is last name equals Smith, or last name equals Joan, or last name equals OA. The OR strategy can be resolved via table scan, multiple match index, or the OR strategy. Short version, table scan, read the table in, filter it, bring the data back. This will happen if we are missing an index or if the cost of the multiple index utilizations exceeds the cost of the table scan. Multiple match index, where key is in 1, 2, 3. Well, this is built for parallel processing and use one process to bring back the 1s, one to bring back the 2s, one to bring back the 3s. And finally, we have the OR strategy, which used to be called a dynamic index. What this does is it retrieves both sets of data. It does a merge join to eliminate dupes. So where ID equals 1 or key 2 equals 2, what if ID is equal to 1 and key 2 is equal to 2? We don't want that row back twice. And we bring the result back. So the next section is index covering, which we've already discussed. So I'm going to skip it because we're kind of out of time. Composite indexes, we've talked about it. composite versus many we've talked about. And this final exam question we've talked about. We've talked about when the index is useful. We've talked about the distribution of the data. We'll talk briefly about index statistics. I'm going to go about another 5 minutes before I take questions, so my apologies for those of you who are running over. It is critical to know the distribution of your data. You can find out what that distribution is by taking a look. This loosely / undocumented DBCC command, DBCC show statistics, will show you what the distribution of the data is, the number of distribution steps, in the histogram, index density, lots of really good stuff to be able to pull out, as well as the last time the stats were updated. If your stats haven't been updated lately, you may not be choosing the best plan. Forcing index selection is generally a bad idea. If you have to force an index selection, there's usually something wrong with the way the query is written. Or your stats are out of date, or you found a bug. If your stats are up to date and the query is well written and run it by somebody else just to make sure, report it to Microsoft as a bug. They do fix these. But if you force indexes because you have to, make sure that every time you apply a patch or an upgrade, you try taking it off and seeing if it'll work with this off, because as the optimizer learns new tricks, you may be forcing an index and keeping it from using the new trick. The syntax to force the index: open paren, keyword index, open paren, name of the index, close paren, close paren. Note, if you ever see open paren, a number, close paren, that is the old approach where we would give it the index ID. That is very bad, because if you drop and recreate an index, that index ID may change. A filtered index was an absolutely brilliant addition by the Microsoft engineering team to the tool. What happens is this: you have a table. You have a table of things that you've processed. There's 1 million of them. Every day you add 1,000, and every day you clean out 1,000. So here's what happens. You say, give me the first one that hasn't been processed yet. But that is an index with almost no granularity, and as a result, you may not choose the index for that. What I can do is say, select from this table where processed equals 0, and they're not processed. We can basically create an index with a where clause associated with it. Very, very cool stuff. So, in order to do this, and by the way, this did not work well in 2008 when this came out, but with 2008 R2 and later, this does work very nicely. We basically say, create the index on the table where, and specify the conditions. Very, very cool stuff. I'm going to slow down for another minute. There are 2 things that you may want to be able to do. First, add indexes that need to be there. Microsoft keeps track in the DMVs of indexes that it thinks need to be added. And this list gets better the longer you are running the server, and gets reset when the server gets bounced. There's a good article there. Note that you do not want to simply go apply all the indexes, because you may end up with 80 or 90 similar indexes on a similar set of columns. If there's overlap, don't do it. You must eyeball these things. There's also a set of tables that lets you count the number of times an index has been used. If I've got 110 indexes out there, well, I can eyeball it and say, okay, I've got an index on A, an index on AB, and an index on ABC. Well, if I have an index on ABC, I don't need the one on AB or the one on A, because I've already got them covered. That's kind of like having a telephone book on last name, first name, middle name, a separate one just on last name, first name, and a separate one just on last name. Doesn't make sense. So use those DMVs to pick that up. Note that we have the ability to do those lookups. Now, if you go to my blog, which is up here, msqlperformance.blogspot.com, I have scripts to define and create those indexes. I have scripts to identify what indexes are not there. I'd like to invite you all to go there, take a look, join. My blog is relatively sparse. I do not blog things like I took my dog for a walk in the park today, What I use my blog for are things that I want to remember. So if I write code and it takes me a little while to write it, it goes into my blog. So creating all the indexes that I need, identifying the missing indexes, uh, identifying how big my tables are without doing select count stars, things like that, all in my blog. Please feel free to steal the code. I do have similar webinars to this one, complete, up on YouTube. Please check out our YouTube channel. For those of you who want my book, which contains all the class materials in a much more detailed discussion than this, list is there. At this point, I'm going to open the floor to questions. And Mike, where do we want to go on this?
Okay, yeah. Well, thank you, Jeff. Great presentation. We have a few questions here. The first one came in right away, and the question is, what is the best way to index tables with large amount of lob data?
Well, you can't index the lobs, so it depends what you have for lobs. If the lobs are like varchar max, what you can do is create full text indexes on them. That's your best bet. If you are trying to do this based on keywords, you may have to do something similar. I don't have a great answer for you. I need something more specific to hang a discussion on.
Okay, let me. I'm going to take back presentation real quick. There's a page here on my screen, and the question is, where is the intermediate page stored? So you have root, intermediate, leaf, and data. The question was, where is the intermediate page stored?
Sure. It depends where you tell it to store the index. So the index structure, if you're talking about a clustered index, the index structure is partially that data page. The data page is the leaf level. But the rest of it is wherever you tell it to put that clustered index. So you can say, create clustered index on and put it on a file group if you want to put it someplace else. But each of those levels is combined into a single structure. You can't go out and say, look at level 1, look at level 2, look at level 3. You can use a dbcc page command to identify them and walk them, but basically those levels are all stored as a common unit.
It's just another level in the tree, right?
The whole tree structure is stored as the common index. So when you go look at the object and you tell it in the file group where to store it, that's basically where it goes. So the index structure is all in one place. It's not in multiple places.
Okay, and then the other one here is setting. It's going back to the index work on where date of birth between. Setting boundaries on the indexes. Can it be relative? Like for instance, can date of birth be between today minus 365 and today, so it can return records for the previous year?
Got it. I'm going to give you a short answer and a longer answer. The short answer is no. If you do that, the problem is you need something of the format column operator constant. If you have date of birth greater than a function call, then at optimization time, we have no idea what that's going to evaluate to. We will usually not evaluate a function at runtime. So what we end up doing is using estimated stats, which does not work to your benefit. Best thing to do is to calculate that prior to running the between, and that way the optimizer will use those values. Now that I've said that, there is a workaround in some situations. So if, for example, you want to be able to say, I just want a part of this column, or I want this column plus something else. Actually, plus something else isn't going to work, but what you can do is you can create calculated columns. If those calculated columns are deterministic, then you can create an index on those deterministic calculated columns. Deterministic means always has the same value. So a date diff is usually not going to be deterministic, but for example, a string function will be.
Okay, that sounds good. Another question: when creating an index, what should the fill factor be?
Good question. Fill factor is one of those things that started out as a great idea, because what ends up happening is that it gives you space in the data pages and in the index levels for rows to be inserted without having to split, because if the page fills up completely, you have to split the page. Here's the catch. The fill factor is not maintained. So you create the index, you have the fill factor, pages start filling up and splitting. Well, the full pages are at 100 and the split pages are at 50. So the fill factor does not get reintroduced unless you drop and rebuild the index or you do a full reorg. That said, the default fill factor, which is, if memory serves, 100, is a special case which says, actually it's 0, which is a special case that says fill the data pages and leave some space in the indexes. I usually don't mess with it unless I have positively identified index contention and or I have positively identified page contention due to splitting. So at that point, you can spread that out. You can work with an 80 throughout or a 70 throughout. It's going to depend on how volatile your data is, how much page splitting you've got, what your OLTP is, whether you're having deadlock issues or locking and or blocking issues. So not a firm answer, but an it depends answer.
Yeah. I actually, when I first got on this job, they had so much changes and the records would grow. I dropped it from the default to 80, and now I've gone back to 100 because we fixed those problems. So, yeah. Another question here: Is it a best practice to always create a non-clustered index on a foreign key?
Let me give a little context to the answer before answering it. To start with, you do want indexes on your foreign keys if you're going to join to them. But the question is, do you want that to be clustered or non-clustered? In general, if the primary way I go after that data, for example, that invoice header, invoice detail, if I'm going after an invoice detail, almost all the time I'm saying, give me all the details for a header. And I really want to cluster on that. That becomes very important to me. But if I have the clustered index someplace else, then yeah, I want a non-clustered index there so that I'm not doing table scale. Did that answer the question that was asked, or did I dance around it?
No, I think it does. Part of it is depends, right? You just don't by default create indexes on all your foreign keys because you could quickly get to a performance impact for your inserts, right? So
exactly.
Well, here's a kind of specific question. Let's see. What is the best column to use for a data warehouse fact table where most of the values are S keys and most of the ordering and date range functions are based on dimension table data? Did that make sense to you?
It's an extremely broad question.
Yeah.
So in general, in a data warehouse, you're going to want multiple indexes rather than just a single index. You're going to want your single index, your clustered index, probably to be on the column that you're going after a large chunk of data the most of the time, and you're going to want to have those columns in the descending order of the from most granular to least granular, so most unique to least unique. Sorry, that's a very generic question. I had to give you a very generic answer. If you want to ask something more specific, go for it. I had my email up on an earlier slide. All of you are welcome to email me specific questions if you like, as opposed to the more general ones that I'm giving. Happy to help.
Okay, we'll take one more. We're wrapping up to the end here. Here's one I think is just in general, and it's a big one. Can you discuss the example of combining two overlapping indexes into one?
Yeah, great value. Let's say you've got one index on AB and one index on ABC. I would, without thinking about it, get rid of the index on AB as long as I don't have any include columns in there that need to be added to the ABC, in which case I'd add those to the ABC. The reason for that is when I have that second index, there's no reason for it because the ABC index can be used for everything the AB index can be used for. But every time I insert, update, or delete, I have to modify that AB index structure as well. In addition, every time I run a query, I have to evaluate one index over the other. So from my perspective, it's an absolute no-brainer to simply drop that index. Again, making sure that you don't have covering there that needs to be added to the ABC index.
Right. Okay. And with that, we're going to wrap up today's presentation. And I'm trying to find one. And I'd like to say thank you very much, Jeff, for your time here today. It was a great presentation. A lot of folks have made comments. I'll send you all the questions, Jeff. But a lot of folks made comments on how great the content was and how much it helped them.
Thank you very much.
Yeah, that's always good to hear.
Thank you all. Thank you for sharing this hour with me. I appreciate it.
Yep. And with that, one of the fun things that we get to do, because we are sponsored by Dell, is we do give out a door prize. And today the door prize goes to David Otterman. We'll be sending him his Amazon e-gift card certificate in the mail today. So congratulations, David. And if you want to be eligible for receiving the gift card in future presentations, please register and provide your information ahead of time. If you registered today, we can't consider that registration for this because we do this last night. And so if you want to do that in the future, please register before the day of the event and you can be on the list for potential winner. Appreciate that. And thanks again, David, very much. Goodbye, everybody. See you in 2 weeks.